right, so
You did a knot.
people who do know me know that I'm obsessed with drawing dots. I draw lots of dots. So here's a picture of some dots. How many dots are there? 25? How'd you get 25? Did you go 1, 2, 3, 4, 5, 6, 7?
Come on.
Is it really 25? Do most people just go 5 times 5? Yeah, that's a good efficient way of doing it. Okay, so that might be a picture of 25 dots. It's not. It's actually a picture of this. It's actually the sum 1 plus 2 plus 3 plus 4 plus 5 plus 4 plus 3 plus 2 plus 1.
That's easy.
Is it easy? I see some people see it because people are doing weird things. People are doing this at me.
It's evil, not easy.
Oh, it's evil, not easy. Is it evil and easy?
Yes, both. Yes. The intersection.
So what is it? What are people doing to see this? Diagonals? So you're saying that's 1 dot, 2 dots, 3, 4, und 5, 4, 3, 2 und 1. Yeah? Okay, I don't really speak German. Okay, that's beautiful. Is that the sum 1 to 5 and back down again? This is very Greek. This is very ancient Greek. Greeks loved playing with the geometry of figures and just getting cool stuff out of it. In fact, what I'm doing is so classical that you may have seen this before, but if I went all the way up to 10 and then back down again, what picture would go with that first? Let me just ask that. Would that be a 10 by 10 array of dots? The diagonals of? So what's the answer going to be then, without doing the arithmetic? 100. In fact, what if I went all the way up to 1,000 and back down again? Quick, you got half a second to answer. What's the answer? Add up all the numbers up to 1,000 back down again.
10 to the 6.
10 to the 6.
A million.
A million.
No, 10 to the 6.
Okay, this is grand. In fact, if I want to be in fact, this is how I teach algebra to kids, but I'm not actually doing it. Because it's very natural to ask, what if I just went up to some number n and then back down again? N squared? So I really can't stand these algebra books that have a whole chapter devoted to what is a variable. If you give it names, it becomes this mysterious object of fear. Just do it. It's very natural to call it n number, and I use n for the number. But this is grand. Add up all the numbers from 1 up to n and back down again, and we have the fabulous formula n squared. All right. Let me ask this. What if I only wanted the numbers from 1 to 5? Because it is a bit weird going up then down again. And you told me this sum was 25. All of it. What if I just wanted the numbers from 1 to 5? Can I see what that has to be without doing? I mean, I know the answer is going to be, what, 15?
Take off 5 and take half.
Take off 5 and take half?
Add 5 both sides.
Add 5 and then...
Take half.
I'll do whatever you like. What would you like me to do? Add 5 or subtract 5?
Add 5.
Yeah, add 5.
So if I add 5 to both sides, I assume, I'll put another 5 here.
Then you get 2 of them.
Oh, 2 of them. So 25 plus 5 is twice my answer? So I guess that means 1 plus 2 plus 3 plus 4 plus 5 is actually 25 plus 5 all divided by 2, which I believe is 15. Yay or nay?
Yeah, that's not what you want.
What do I want? Is that what I want?
Oh, that is what you want. Okay.
Yeah, it's okay.
Yeah.
I want to add up all the numbers from 1 up to 1,000 and leave it at that. Not bother coming down again.
Do the same thing.
Okay, add 1,000 both sides. There's 1,000 squared plus 1,000. So that'll be double what I want, half of that. In fact, if I want to be very algebraic, because I don't like writing actual numbers, sum of 1 to n. Yeah, add an n to both sides. N squared plus n. Double what I wanted.
And then you've got the famous formula.
I believe that's a famous formula. Wow. Now, I'd like you to memorize that formula and do these 50 questions tonight for homework and then do some push-ups. So I have a snide attitude about education. Well, that's pretty powerful. So what's the sum of all the numbers from 1 up to 1,000,000?
Same thing.
Well, who wants to actually
10
do
to
it? You
the
say 1,000,000
11.
squared plus 1,000,000.
No, 10.
Half of that. Yeah, perfect. Good answer. Well, what is 1,000,000 squared?
10 to the 12.
Million. Trillion? Okay,
Depends, are you English or are you
Yeah,
American?
here's the issue. Here's an issue. I can't resist. What do you call that in the US? 1,000. What do you call this in the US? Million. What do you call the first one in the UK? I'm not British, by the way, I'm Australian. But what do you call it in the UK?
Disclaimer.
1,000. What do you call this in the UK? I know you're nervous. Million. What do you call this in the US?
Billion.
Billion. What do you call that in the UK? 1,000 million. What do you call this guy in the US? So you guys go 1,000 million, billion, trillion, quadrillion, da da da. But in the UK, it's 1,000 million, 1,000 million, billion, 1,000 billion, trillion. I would much rather be a billionaire in England for two reasons. What are the two reasons? Exchange rate way better. Plus I'm up by a factor of 1,000. Anyway, I digress. Oh, so that's all grand. Actually, let's be very Greek. Let me go back to what I first did here. 1 plus 2 plus 3 plus 4 plus 5. When I did, whoops, all the way up and down again, that was the whole square. What's the picture that goes with just 1 plus 2 plus 3 plus 4 plus 5?
Triangle.
It's basically half the sum, isn't it? Actually, it's a bit more than half the sum. So it should be half that square I'm hearing. I heard people say the word triangle. Is it a triangle?
Yeah.
There's the 1, there's the 2, there's the 3, there's the 4, there's the 5. So I'm only looking at this part of the picture. So it's getting very messy now, sorry. Yeah. People call that a triangle number. In fact, the Greeks would love to draw things like this. Let me just get that picture very messy. They make it look more triangle-y. Do you see 1 plus 2 plus 3 plus 4 plus 5 in that picture? That was called the fifth triangle number. Grand. Lots of jolly fun. In fact, we found a formula for the nth triangle number. It's gone from the board, but I did ask you to memorize it because memorizing is important. What was the formula again? Okay, n squared plus n divided by 2. All right, you said the trouble is I've been lying for the last 10 minutes. My original picture was not that sum, I'm sorry. All this is a lie. This is actually a picture of this. Am I right or am I wrong?
Right both times.
1 plus 3 plus 5 plus 7 plus 9. What do you think? Now, kids would often just do slodgy things. They'll go 1 dot, 3 dots, 5 dots, 7 dots, 9 dots. Which is really equivalent to just going 1 plus 3 is 4, plus 5 is 9, plus 7 is 16, plus 9 is 25. But what's the sort of the nice, beautiful way to see this? This is why I get to the beauty of mathematics. I don't want to say random, I'm saying it feels powerfully gorgeous.
3 dimensions.
3 dimensions. I mean, follow the L's. Is that what you mean by L?
Yes.
Oh, somebody, okay, sorry, I started completely the wrong place. It's not going to work till I said. Oh, you're right, sorry. So that's 1 dot, that's 3 dots. Is that 5 dots? Is that 7 dots? 9 dots? By the way, what's the, I mean, I don't know why I'm saying this, but what's the official math name for an L shape? Yeah, it begins with a G. You seen that word? How to impress your friends at Scrabble? No. It's actually the name of the L-shaped piece in the middle of a sundial. That's where it actually comes from. Anyhow, so there it is. The sum of the first 5 odd numbers must be a 5 by 5 square. What's the sum of the first 10 odd numbers then? 10 by 10, 100? What's the sum of the first million odd numbers?
10 to the 12.
Would that be a million squared? Now here's the hard question. What is the millionth odd number? Ooh.
1 million.
What is the millionth odd number?
1999.
Is it 1
2,999,000.
999,999, or is it 2,000,001? Or is it 999,999? Or is it 1,000,001? Oh, I hate those questions. They're really annoying. It's like one of those questions like, my history teacher's going to make me read pages 40 through 50 tonight in the book. How many pages do I actually have to read? It's one of those type of questions.
It works out well because my students always do it wrong, so they always think they have one less homework assignment.
Excellent. All right. That was just the warm-up. I went pretty fast. This is very classical stuff. People know me. You've probably seen this 1,000 times. What you haven't seen, what I really want to talk about, is this guy. What have I drawn? Multiplication table. In fact, I've done the actual numbers there, just order multiplication, and then I've said what they are. This one's really 3 times 3, that 9. This one's really 1 times 5, that 5. Great. So when I was in primary school, back in Australia, we had to memorize our multiplication tables up to the 12 times. Is it 12 times in this country? Is it not 10 times? 10?
It depends probably.
Probably varies. Okay, 10 or 12. I was really jealous of Peter Sylvester. He could memorize his tables up to 14 times tables. That was a big deal back in grade. What grade is this? I don't know what grade this is. 3, 4? Yeah, I was impressed with Peter. He could do his 14 times tables. Just as an aside, if we're going to make kids memorize stuff, do you know you don't actually have to memorize beyond the 5 times table? For example, what if I want to do something like 7 times 8? I'm going to teach you a handy trick. A closed fist is worth 5. To make it 7, add 1 more digit, number digit, that's now 7. This closed fist is worth 5. To make it 8, add 3 more digits. So you got my stuff? This is going to be 7, this is going to be 8. Each finger up is worth 10. Because I've got 10 fingers in all. So I currently have 5 fingers up. That's 50. And all you have to do is multiply the fingers down. There's 3 down, there's 2 down. What's 3 times 2? 6. I claim that 7 times 8 is 56.
Oh. So how about I go with that?
Want to do another one? 9 times 8. What's 9?
4.
What's 8? All right, each finger up is worth 10. 70. Half us actually counting, yeah. And you multiply the fingers down. 1 down, 2 down. What's 1 times 2? So I do need to know that table. 1 times 2 is 2. 72.
So do 12 times 11.
Okay. I will use my fingers and toes to go beyond the 10 times tables. But before I do, I want to make sure we understand just the fingers. What about these?
Numbers aren't bigger than 5.
Sorry?
Like 9 times 4.
9 times 4, so you have to anti-raise a finger on this end. Okay, there's problems. I'm with it. I'm with it. Does it work in extreme? What's 10 times 10? And 0 plus 0 times 0? What's the other extreme? 5 times 5 would be the, in this case, yeah. Is it working?
Yes.
It didn't. Or each finger up's worth 10, nothing. Multiply the fingers down. You actually have to know 5 times 5 is 25. Alright, so this is actually a great question. Why on earth is that working? Or was it just a coincidence that I was just pulling up ones that seemed nice? And my Algebra 2 kids either completely love me or completely hate me, because this is the sort of thing that actually motivates good algebra questions. And in fact, let's go beyond 10 times 10, just make this worse. Let's do 17 times 18. Okay, and I'm going to use fingers and toes. I've got 10 digits on this side of my body. Everything down is worth 10. To make it 17, I'm going to put up 5 toes, which you can't see, and another 2 fingers. 7 digits up on this side. 18. Everything down is worth 10. To make it 18, put 5 toes up, 3 things up. So 18 up. Now, since I'm using all 20 digits, everything up is now worth 20. So I've got 7 up on this side, and 8 up on this side. So each is worth 20 makes 15 20s, 300. And you multiply what's down. 3 down on this side, 2 down on this side. What's 3 times 2? 306 then. Is 17 times 18 306?
Minus 34.
Fortunately, you just did say that.
Oh, thanks to goodness I just said my 8 for us, yeah.
Yeah, I'm sorry.
Is it? I don't know. Anyone calculate? Let's do it that way. Of course it is. Fingers and toes are telling me it is.
Oh,
Want to do another one? 19 times 16. Think your way through it. Oh, we did the same numbers again, kind of. 19 times 16. How many digits are up? 15. Toes, don't forget the toes, you can't see them. Let's switch those 300 again and multiply what's down. 1 times 4, 304. Is 19 times 16, 304? Actually, I'm being a bit cruel. I'm throwing too much stuff in our way. I don't normally hit you with all sorts of things, but this is actually a great puzzle unto itself. Why on earth is this working? And then my brain is like this. I happen to know that Martians don't have 5 fingers in each hand. They have 6 fingers in each hand. So what on earth are Martians going to say about this and do? So I'm going to be cruel. If you want to figure out this finger trick, feel free. It's a, you know, the math is sort of figure out how to write down an equation to describe what we're doing, and then some little algebra. Or you can just go to, just look at my stuff. JamesTanton.com, and if you look on that website and just hunt for a finger trick, I reveal everything. That's the cheating way to do it. But what I really want to do is play with this multiplication table. And let's do it in a very Greek way. We did 2 things with the dots. We added up diagonally, we added up in moments. What if I add these numbers up diagonally? There's the 1, there's 2 plus 2. What's 2 plus 2? 4. 3 plus 4 plus 3. 4 plus 6 plus 6 plus 4. 5 plus 8 plus 9 plus 8 plus 5. 35. I guess I'm going to stop there because technically my table keeps going. I'm missing those numbers, but I could keep going. So here's my first question. What are these numbers? 1, 4, 10, 20, 35 that would keep going if I had more space on my table? What are they? So my 35 is very scrawlily written. 1, 4, 10, 20, 30. In fact, do you have a prediction of what the next number is going to be without actually working it out? We predict 56?
56.
Would you like to know if it is 56 or not? Actually 56, I can tell you because I don't have it in my head. Maybe not, okay.
I don't know.
Yes.
Yeah, it is 56, turns out to be the next number. All right. Mystery number 1. That was the diagonals. Let's do the G word. What's the G word again? Gnomons. I'll do them in rune. There's 1. What does that gnomon add up to? 8. What does this gnomon add up to? 27. My handwriting truly is atrocious. The next gnomon. Is it 64? That's what I'm hearing. Is that actually 64? I'm lazy. I see a 20, and 20, and a 20, and a 4, 64, okay. Do you know what? Actually, that's what I really wish I could ultimately teach kids in high school. Just be clever. Save yourself work. How to be lazy. How do I be lazy with that gnomon? Maybe 20? I mean, I don't know. It's your style. It's your gnomon. 20, that's 50 there. And 50? 75? No. Okay. Now I guess my second mystery is, what are these green numbers? Cubes. Okay, we feel like we can recognize them. 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed. So you predict for the next one, 6 cubed, and then you probably check yourself to see if you're on track. Alright, so now we have 2 mysteries. One I feel I've got more of a handle on. Green ones seem to be cube numbers. Red ones seem to be some numbers. Could we... I guess the red is going to be meatier because we have to, first of all, figure out what those numbers mean and then explain why it's true. We know what these ones seem to mean. Is there any reason to believe why those gnomons should be cubes added up together? Yeah? Okay, that was the yes/no question I asked. Yes, there is a reason to believe there should be cube numbers. Well done. Is it the previous problem?
Related.
No way.
Because we're adding up the numbers and like the fifth gnomon, we're adding up the numbers and multiplying by 5.
Alright, so let's actually look at this fifth gnomon then. So you said the fifth one, so that should be 5 cubed. So somehow I should see, do it this way.
It's 5 squared times 5, of course.
Is it 5 squared times 5?
Yeah, because it's the, you can factor out the 5 from all of that.
Alright, so I'm going, okay, that, what's that, what's that, what's that, what's that, what's that, what's that, I'm hearing factoring out the 5, so it's really 5 times, what, 1 plus 2 plus 3 plus 4 plus 5.
And then you get the rest of it, yeah.
And do we recognize this beast? So it's really 5 times 5 squared, so it's really, well, 5 cubed. Is that specific to the 5, or is that going to work for the nth gnomon as well, just in general? Oh, gosh, you guys got that right. That's brilliant. Well done. Right, so what are these red ones?
Oh, right.
They're the triangle numbers? Yeah, what are the triangle numbers again? I'm going to do this. No, I'm going to do this. So here are the triangle numbers. Oops. Not very good triangle, sorry. That was 1 plus 2 plus 3 plus 5. I remember it was 15, we said. 1 plus 2 is 3. 1 plus 2 plus 3 is 6. 1 plus 2 plus 3 plus 4 is 10, 15. So you're telling me these red numbers are related to those green triangle numbers? 1 is 1. 4 is 1 plus 3. 10 is 1 plus 3 plus 6, is that right? So is that hearing you say it? 1 plus 3 plus 6 plus 10 is Sansi? Yeah? Okay. Pyramid numbers. Someone said 3D earlier on. Maybe they really want to go 3D. Is it 3D? How do you think this is 3D?
stack them up.
You know, we all must think terribly alike, because guess what I had to do before I came here? Actually, I've just revealed a very interesting math circle issue if you want to do one of these things. Obviously, I had a feel of where we're going to go with this class. And you don't know how many transparencies I have. Maybe I have a whole like branching possible sets depending on where we go. Or maybe I kind of knew would end up here, and that's the only transparency I made for this section. And I just somehow cleverly made us guide our way that way there. I don't know. What did I do? Yeah, meta questions don't count. Is that really a sum of triangle numbers? Let's just be very clear. Do we see it? You see one little tiny lonely triangle number there? 1. 1 plus 2 makes 3. 1 plus 2 plus 3 makes the 6 there, and so on. Oops, that's there. So I think I've done the 5th one, right? 1, 2, 3, 4, 5 layers. All right. So apparently, the numbers, which were 1, 4, 10, 20, 35, 56, seem to be these pyramid numbers. I guess people tend to call them tetrahedral numbers. If you're especially a Greek, what does tetra mean? 4. So where's 4-ness in this? 4 faces. It's a 4-sided pyramid. Does that make sense? Okay, so a lot of mathematicians call these the tetrahedral numbers. The Greeks will call them tetrahedral numbers. We can call them pyramid numbers. Actually, I don't care what we call them. All right, so the question is, why on earth would the diagonals of a multiplication table correspond to 3-dimensional stacking of triangles to make tetrahedrons? 1, 4, 10, 20, 35. I can write out the products. My terrible board technique. One, 4, 10, 20, 35, and somehow it's got to do with a tetrahedron. Is it all fitting? Of course not.
Slide the one that you wrote on up.
In fact, I think this tetrahedron is the 5th one, so apparently that whole figure has 35 dots in it. But there's no way to naturally see, of course it has to be 35 dots.
It's slightly more than half of the nomens, just like the previous triangle numbers were slightly more than half of
Ah. So, how do I translate that then? Slightly more than half the nomens, like the triangle numbers, slightly more than half the squares.
Right.
So this whole picture is slightly more than half of something?
When the nomens gave you a cube,
Yep.
what we have is the cube cut along the diagonal, including that diagonal. That's where the slightly more than half comes from.
Oh, so you're saying then, if I took another one of these guys and sort of stuck it on that side, this represents basically half a cube.
Yes.
In which case, and that face there is like double counted, like we had the double diagonal. All right, true. Is it really true if I took 2 tetrahedrons like this and stuck them together like that, would be a cube?
If you smoosh it.
If it's, okay, smushed up cube? How many faces would our object have? And how many faces does a cube have? 6. So these numbers are slightly more than half the matching cube number. Is that what you're telling me? Yeah. You can't see at the front, but lots of people like giving me frowny things at the front here. don't know if that's... I don't know if they have frowns like they vehemently disagree with you, or maybe they have frowns like I can't see it yet and I'm just frustrated with myself. Is it true or is it not true?
So it's actually less than the cube, so it's kind of there.
It obviously has to be less than the cube, but less than half the cube in fact. In fact, I think the trouble is it has to be less than half the cube by a triangle number of stuff, and that's kind of hard to... It keeps changing how much less by it is, I guess, depending on the size. Oh yeah? Oh, what do you mean we'll slice it this way?
The 5 on the bottom edge there. Just slice it.
Oh, okay, so, oh. You really want to go for the 5 ones. And here you said the bottom edge.
You mean for the long 5 on the bottom edge?
Here's 5 ones. Four 2s or 2 4s? I guess that's which way we're reading this. I'm sorry, you have 1 5. Now I want to see 2 4s. This is going to be a mess now. Behind the 5 and above it. This is going to be a really terrible mess picture. Is that a 4x2 rectangle? In some sense, this is a 5x1 rectangle. Is that a 3x3 rectangle? Middle school teachers might yell at me right now.
Yeah.
Yeah? Yeah?
The next layer.
Oh, hard to draw. 3, 1, 2, 3, is it?
Yeah.
Okay, there you go.
And 1, 2, 3? Or something. Beautiful, look at that. Perfect. Is that 3x3 if I'm kind of doing it? And what about 4x2 or 2x4? I've lost which way we're going. Seeing it? 2 and then sort of come down.
Well,
It's hard to picture in my drawing, I'm being a little bit bad with it. And what about 5x1? Oh my goodness. I believe this diagonal really is a stacking together of slices that end up making the 5th tetrahedral number. Purely visual proof. Do you think it works in general? I mean, that was specifically 5. Do you think we're onto something that works in general, or is this just we lucked out this particular size we have? Yeah? Then I'm with you. These numbers are the tetrahedral numbers. They come from stacking triangles. That's why I think you said to me, you notice the difference is like up 3, up 6, up 10, like sums of triangle numbers. It's all fitting together. I can see sums of triangle numbers, and if I look at the clever way of slicing, I can see products like this. Obviously the diagonal is a multiplication table. Brilliant. Very nice. Very Greek. So then here's my next question. After your success of brilliance, you get yet another question. What's the sum of all the numbers in that table? And we do it all by hand and actually add them up? Or is there cleverness to be had?
Do that.
Some, ooh. And what makes you say some are cubes?
Because you want to add up the L's.
So one way you do it is add up all the L's. That would definitely give me the sum of all the numbers in that table and add up all the L's, is that right? So the answer must be, each side that's 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. Okay, that's the answer, what that is.
You can also also factor out
Or you can also do something else apparently. What can we also do?
You factor something out, then you get 1 plus 2 plus 3 plus 4 plus 5.
Oh, if you go by rows, we know 1 plus 2 plus 3 plus 4 plus 5. That was, that formula I think was 5 squared plus 5 over 2, you told me?
So it should be the square.
And then you factor 2 out of that, and you get the same thing as 2.
2 times
And so
1 plus 2 plus 3 plus 5, is that right? So I'm going a little fast now because I realize time is now not our friend. Is this 3 times the same thing? What's this guy? 5 times 1 plus 2 plus 3 plus 4 plus 5? Alright, that looks charming on the right. Well, I guess that's 1 times, and also it's symmetrical. Yeah?
But you can also see it as 1 plus 2 plus 3 plus 4 plus 5 squared. Because when you square it, you get all of those products.
Pull out this common horrible factor. We need a different colour. We need black. We're now serious. It's 5 squared plus 5 over 2 times 1 plus 2 plus 3 plus 4 plus 5. Which is what? So this is 5 squared plus 5 over 2 all squared. Oh my goodness. In fact, if you had to hazard to guess, 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed.
that's the sum of the first n cubes.
That's the sum of the n cubed. Here we did the sum of the first 5 cubes, and we got that beast.
N square.
N squared plus n over 2, one of these horrible factors. Squared. Now, since I am a high school teacher, this does come up in a few places in the high school curriculum. Oh yeah?
But I was just saying that it's pretty much what you did, but another way to see it is that if you write down 1 plus 2 plus 3 plus 4 plus 5 and square that, then what you're getting is all products of one of those numbers by another one of those numbers, which is what's in the table.
Way. Whatever floats your boat, it's good. All good math is good. Brilliant. This comes in 2 places. Often some curriculums will have kids teach deduction. They make them prove formulas like this by deduction, and it's just the most dry, joyless way. It doesn't explain where these formulas come from, who thinks of these things in the first place. This is just beautiful. In a basic calculus class, they'll often give formulas like this because you want to do your basic area under y equals x cubed or something and do little rectangles. You're stuck with summations of things like that. It's sad to me that this is kind of the joyous way to sort of play with this idea and look what's just magically appeared. I had no intent, well, I'm dead, but I'm pretending I had no intent to get there, and there it happened. But it does leave you with a second mystery, though. Today, we've seen this. And we've now just seen this. So what's the sort of mystery to be had? This seems to be the compelling question to me right now. And clearly it's got to be something between that answer and that answer. So I'm proposing this. What do you think? Well, clearly it's halfway between. Well, I'm afraid that's it for the timing, what we can do today.
Oh, we have to do that as homework?
Oh, this is the quiz. This is the quiz, yes. We got a form for that guy. And be clever. If you really have to do, well, you can't even do induction, you don't even know what the formula is, so that's the trouble with induction, that's the grungy way of getting things. I guess you just, on your own, be very Greek, draw some pictures. By the way, I'm going to be obnoxious. We've got all the tools, what we've seen today, to make it happen. Do things with tetrahedrons some more. Maybe slice up yet a different way. Maybe things will sort of gel, play. And that's the nature of math circle, play. It doesn't matter to be wrong, you're meant to fumble, you're meant to flail, you're meant to feel like you know nothing. So welcome to the real world, you know? And every now and then those little epiphanies will happen after the weeks of struggling. And those little epiphanies are so joyous they compel you for more, even though it was weeks of suffering. And we often don't teach kids the patience to suffer and the tenacity to push on and just go forth and just find joys where they happen and follow different tracks. We always feel like we need to get to an answer, we need to get to the answer quickly. That's not fun. This is hard, but it's also fun. This is maths over world. All right, so thanks so much. Thanks for coming along.